Hello! We introduced the Knapsack auction last time. The main issue with Knapsack auctions is that it is difficult to find a welfare maximizing allocation rule efficiently. We still want to keep efficiency. So the goal now is to efficiently approximate the welfare maximizing function for the Knapsack auction. We can then use Myerson's lemma to find the payment rule. As an aside, typically with approximation algorithms, we want some performance guarantee. This has the form the solution produced by the algorithm must be at least this close to the theoretical optimal. Let's first look at the intuition behind solving the knapsack problem. Take a look at this example from last class, where we have 4 items with different T and V's. The size of our knapsack is capital T, which is 10. The main idea is that we have limited space, so we want to fill in each unit of space in our knapsack with as much value as possible. So this leads to the idea of calculating the value density of each item. Higher density should give us better value. We can sort the items in non-increasing value density, from item 1 down to item n. In our example, we have these value densities, and they are already sorted. So a natural idea is then, we pick as many items with high value density as possible. So as our first try, we pick items 1, 2, etc. until we cannot put the next one into the knapsack. In our example, we can pick items 1 and 2. They have a combined size of 9, which fits into our knapsack of size 10. Then we have no room for item 3. So our total value here is 76. This sounds like a very simple algorithm. But does this always produce a good approximation? And the answer is no. There are cases where the solution produced is very bad. So consider the example where we have 2 players. For player 1, V1 is equal to T1, which is equal to 1, which has value density 1. For player 2, V2 is T minus 1, and T2 is T, which has value density less than 1. So the first one has a higher density than the second one. If we pick 1, then we do not have room for 2. So the algorithm produces a solution with value 1. There is an obvious optimal solution here, just pick 2. And the optimal value is T minus 1. So our solution is 1 over T minus 1 of the optimal, which could be arbitrarily bad. So here is a better idea. Suppose we stop at item I in the algorithm above. We can check the value of the next item, I plus 1. If its value is strictly greater than the sum of all the items we have so far, then we will abandon all the items we have picked and pick only I plus 1. So I plus 1 is the only winner in this case. For this to work, we will make a reasonable assumption that Ti is at most capital T for all I. In our 2-player example above, we will stop at I equals 1. We see that V2 is greater than V1, so we will pick V2 instead. And here is the full approximation algorithm. We assume n items, ordered with their value density. We find I such that it is the largest index with a sum of T1 to Ti at most T. If the total value of these I items is at least the value of the I plus first item, then 1 to I are the winners. Otherwise, only I plus 1 is the winner. We claim that this is a pretty good approximation to welfare maximization. Suppose APX is the value of the winners produced by the approximation algorithm, and opt is the actual optimal value. And the theorem we want to prove is that APX is at least half of opt. This means that the solution produced by the approximation algorithm is guaranteed to be at least halfway to the optimal. And here is our proof. A welfare maximizing solution is optimal for this integer program IP, which is max of V transpose X subject to T transpose X is at most T, and each Xi is either 0 or 1. The optimal value is opt. Its LP relaxation is the same thing except now Xi is between 0 and 1. So now solutions can be fractional. We let I be the largest index with the sum of T1 to Ti at most T. This is the I produced by the algorithm. We now consider the following solution. X1 to Xi are all equal to 1. Xi plus 1 is T minus T1 to Ti divided by Ti plus 1. And the remaining x's are zeros. The meaning of this is that we fill in our knapsack with the first I items, and then fill in the remaining space with a fraction of item I plus 1. In our 4-item example from earlier, we would have x1 is equal to x2 equals to 1. We then have a space of 1 left, so 1/3 of item 3 can fit in there. So x3 is 1/3, and x4 is 0. Now, as we have completely filled the knapsack with the highest density items, x must be optimal. Note that this is not a rigorous proof, so as an exercise, prove that x is optimal formally using duality. We now suppose that the optimal value of LP is V star, which is obtained by our x above. Recall that opt is the optimal value of IP. So what is the relation between opt and V star? Remember from your optimization course, since LP is a relaxation of IP, opt is at most V star. That is because any feasible solution to IP is a feasible solution to LP. So we want to prove that APX is at least V star over 2, which would then prove that APX is at least 1/2 of opt. We let S be the set 1 to I. We see that V star is at most V1 to Vi plus Vi plus 1. The value of our LP consists of the first I items plus a fraction of the I plus first item. And this is equal to V of S plus Vi plus 1. We now look at two cases. If V of S is at least Vi plus 1, then the algorithm picks S. So APX is equal to V of S, the solution of the approximation algorithm. So V star is at most V of S plus Vi plus 1, which is at most V of S plus V of S, which is 2 APX. In the second case, if V of S is strictly less than Vi plus 1, then the algorithm picks I plus 1 only. So APX is equal to Vi plus 1. Then V star is at most V of S plus Vi plus 1 is strictly less than 2 Vi plus 1, which is equal to 2 APX. So in all cases, APX is at least V star over 2, which is then at least 1/2 opt. And that completes our proof. So we have an approximation algorithm for welfare maximization. We still need to show that it is monotone before we can apply Meyerson's lemma. and we will leave that as an exercise. Now, Meyerson's lemma gives us a payment rule for our allocation, that is DSIC. So now we want to know, what is this payment rule? What does the allocation function look like for a particular player? It is like a single item auction. A player either wins or not. So the allocation function looks like this graph. Say this is for player J, and there is one jump that occurs at BJ bar. The payment for winning is then BJ bar. So how do we find this value BJ bar? We could use binary search, or we can use some logic to figure out what this value is. Take a look at our starting example with 4 items. The approximation algorithm will pick 1 and 2 as winners. So what is the payment for player 2? We know that the allocation is monotone. So to find B2 bar, we need to lower V2 until the approximation algorithm does not pick player 2. Now notice that as long as the value density is at least 7, the algorithm will pick 2. So player 2 can go as low as 49 and still win. Now, what happens if V2 gets below 49? Could it still win? Say it has value density at least 5. The approximation algorithm will pick 1 and 3 with combined value 41. Then we will look at V2. If V2 is strictly larger than 41, then the algorithm will still pick 2. If V2 is at most 41, then the algorithm will stick with 1 and 3. So our jump point, B2 bar, is at 41, and the payment is 41. And this concludes our discussion on ideal auctions.